All right, so this lesson, which again, it's chapter 7 from the text, it's our lesson 5, it finally stops talking about making molar solutions and starts talking about what can we do with those molar solutions. So let's just say hypothetically, we make a molar solution, a molar solution of some acid, and we make a molar solution of some base. What's going to happen in the event that we mix those two solutions? Okay? And so the first question we're going to address is this one. What is a chemical reaction? What is a chemical reaction? So what I want you to do right now, I want you to talk to those around you, and I want you to come up with evidence that a chemical reaction has taken place. What is something that would happen that would convince you that chemistry has happened? Okay? That something very unique has happened, right? It's very different than, you setting an ice cube on a table and it melting. Okay? Although that's cool. And if you leave it there long enough, it will all evaporate. Although that is cool, it's not a chemical change. Okay? Chemical reactions require chemical changes. So what is something that would clue you into a chemical reaction has happened? All right? Take a minute or so starting now. All right, to help you inform you as you continue this discussion, I'll tell you a little bit about what a chemical reaction is. Opposed to physical changes, chemical reactions involve atoms moving from one molecule to another. So there has to be some kind of a rearrangement of the atoms from what you started with to what you end with. If a chemical reaction has taken place, you need to move atoms from one molecule to another. That's why ice melting on the tabletop is not a chemical change. Because your water molecules, yes, they're moving from being locked into a solid into being more free to move, but the atoms are not changing. It's still water. I don't know if you knew that or not, but ice is water. And water is liquid ice. Ice is solid water. All right, so go ahead and continue this conversation for a little bit and give me some evidence that a chemical reaction has occurred. Or are you all done? Did you all finish that conversation? Okay, so what are some evidences that a chemical reaction has occurred? How would we know that an atom has moved from one molecule to another? What are some clues? Explosion, right? Unfortunately, not all chemical reactions involve a dramatic release of energy, but some of them do. Okay, and it's a very obvious, it's a very obvious sign that a chemical reaction has taken place when you get an explosion. You're like, what about if there's just a bomb? It's still a chemical reaction. Okay. Yeah. Any other evidences? Change of color. Yeah, and so another clue that atoms are changing molecules is you're making something unique and new, and it corresponds to there being a color change. Absolutely. Any other ideas?
It goes from a liquid to a solid.
Does not go? Is that what you said? Goes from a liquid to a solid. In some cases, but in a lot of those cases, those are physical changes. Converting from a liquid to a solid or from a solid to a liquid. All right. So a little bit more information on this. Basically, in a chemical reaction, the reactants are converted into products. So we write a chemical reaction like this, where we have our reactants on the left and they are converted into products. And the reason why we put our reactants on the left is because in English we read left to right. And so this tells us that we are starting with this material, and at the end of our chemical reaction we have this material, or these materials, it's more than one, okay? So that's how we illustrate a chemical reaction. The way, again, that we know something has happened is like a dramatic release of energy, or a color change, or maybe a dramatic absorption of energy, right? Sometimes reactions feel really cold. And we'll do some of this in our next lab. We'll carry out some of these common reaction types. You'll be able to feel a reaction that requires an enormous amount of energy, and it will feel very cold, even though you mix two materials that were at room temperature. And then all of a sudden it feels very cold. It's kind of cool. It's one of the things that they use to make some ice packs. You know, where you, like the ice pack doesn't feel cold, you crack something, and then there's a chemical reaction that pulls a bunch of energy out. It's cool stuff. All right. Now we use a study called kinetics to study the rate of this reaction. Because it's one thing to know and to say, okay, a chemical reaction is taking place. It's another thing to say, okay, during this chemical reaction, we converted these materials into these materials. It's an entirely different thing to study the rate at which this reaction takes place and what factors might change that rate. And that's what kinetics is all about. Because we want to know what factors are going to change the rate of reaction. What's a chemical reaction that you might want to speed up? Can you all think of something? Yeah, Tom.
An explosion.
An explosion. Why might you want to speed up the rate of that reaction?
Well, if you want to make it more powerful.
Sure, if you want to make it a more dramatic. And you're like, well, in this context, I mean, think about in terms of demolition, right? Explosives are used a great deal in demolition projects, okay? Have you ever watched them blow up an old massive building or an old stadium? Watch one of these demolition projects. Enormous amount of explosives used in that process. And so some of these reactions, yeah, you want to speed up the rate of reaction so that it can happen more quickly and efficiently, means it requires less money. Okay? So some of these reactions are spontaneous. Some chemical reactions are spontaneous. What does that word spontaneous mean? Immediate. In some context, Tom.
They don't need to be triggered by anything.
Yeah, it's without cause, right? If you say somebody's a spontaneous person, they tend to make decisions without cause, right? They do not random things, but they do things that are without cause, like maybe change jobs all the time, not because they have to, but just because they want to, right? Or move all the time, or get new things all the time. It's right, this idea of without cause. And so a chemical reaction that is spontaneous, what does that mean? It means you don't have to force that reaction to happen. You don't have to input energy to make it happen. It's going to happen. Okay? It's going to happen. It's spontaneous. It's going to happen without cause. Okay? Now, one thing you need to know is even spontaneous reactions require some activation energy. And I'll show you what that means. I'll show you what that means. So go ahead and write that down. Sorry, that was louder than I anticipated. Go ahead and draw this graph for me. And on this graph, we have energy on the y-axis and time on the x-axis. As you move away from the origin, which is here, energy increases. As you move away from the origin here, time increases. Now, looking at a chemical reaction, at the very beginning, what are we going to have? Reactant or product? Reactants, right? So reactants should be towards the left of this, because at the beginning, which is going to be at the origin, we're going to have reactants. Okay? And then over here, as we move right on the x-axis, we're going to have, our products. Now, looking at our graph, what has more energy, reactants or products? Reactants. How do you know? Because it's higher up on the y-axis, right? And as you move away from the origin, energy increases. So this would be an example of a spontaneous reaction, okay? Where the reactants contain more energy than the products. This is going to tend to be a spontaneous reaction, meaning you don't have to invest energy to make it happen. It will happen, and it will actually release energy as it does. However, something has to happen in order to facilitate the reaction. The reactants need to come together, right? And so there may not be any way to get them to come together in an efficient way other than to invest a little bit of energy called activation energy to force them together. Okay? So just because it's spontaneous doesn't mean that it's just going to happen really quickly, right? It may happen, but it may take millions of years for you to wait until those reactants come together in just the right way. And if this is a reaction necessary for living organisms, you cannot wait millions of years, right? True or false? I will live a million years. False. Meaning the cells in my body cannot wait millions of years for a reaction to take place. So which means they have to invest some activation energy to force these reactants together, because the cells can't just wait for these reactions to happen. So there are materials that are called catalysts. In cells, these are usually enzymes. They aren't always. There are other catalysts in cells, but in cells it's usually enzymes. Lower the activation energy, and therefore they speed the rate of reaction. Okay, they lower the activation energy and therefore speed the rate of reaction. And sometimes on the degree of millions of, or they can speed it up 1,000,000 times or more. All right, now we can talk in a little bit, if you want, about how the catalysts lower activation energy, especially enzymes in cells. But some of that is beyond the realm of this course. But if you want to talk about how that works, we can. Just remind me, and we can talk about that at a later time. All right? Does this make sense? So a chemical reaction involves atoms changing from one molecule to another. Some of these reactions are spontaneous, meaning that they will happen, but the rate could be very, very slow. And so kinetics, studying what can increase the rate of this reaction, one of those candidates are catalysts that lower the activation energy to create, or not to create, but to facilitate carrying out this reaction much more rapidly. So I want to answer this question now. There are a couple more points on the slide to discuss, but I want to answer this question now. So what is a chemical reaction? The best way to answer that is going to be this. It is a process, comma. It is a process, comma, in which atoms change the molecule in which they are found. Period. In which atoms change the molecule in which they are found. period. Or say process, comma, in which atoms are moved from one molecule to another. That might be a better way to say it grammatically. I don't remember exactly what I said on Monday, so Monday class you may have a slightly different way to answer this. All right? Make sense? Okay, a couple of key terms I would like for you to look up: kinetics and spontaneous. Okay, make sure when you look up spontaneous, you put in chemistry along with that. Otherwise, you'll just get a general definition of spontaneous. And I think on Monday I had them look up spontaneous and catalyst, but we'll have you all look up kinetics and spontaneous. As you define kinetics, you're going to get a reference to catalysts, speeding up the rate of reaction. All right, so last couple of points. What is metabolism? So what I'd like for you to do is take about a minute or so, maybe as much as 90 seconds, and I want you to come up with a definition for metabolism based on what you've heard. Okay? Based on what you've heard or what you've been taught. Have you ever heard somebody say, I have a quick metabolism, or I have a fast metabolism, or I have a slow metabolism? Have you ever heard that? Okay. So take about a minute or so, see if you can come up with a definition of what metabolism is. All right? Minute to 90 seconds starting now. Is this bothering you? Now is it bothering you? Okay. All right, so do we have some ideas? Anyone have some ideas that wants to offer up their definition? Tom.
So I thought maybe it's the process of turning matter into energy.
Okay. Let's phrase it this way. Let's say the process of converting the form of energy. Because there's still energy in matter, but it's in a form that's called chemical potential energy. And we'll talk about that in a little bit. And we'll actually talk about laws of energy. And so we can't convert matter into energy, but we can release the energy within that matter. And so what's happening here is if our reactants are higher energy than our products, there's energy stored in bonds. And we'll talk about bonding a lot. And as we break those bonds, it releases energy. Okay. Yeah, I like that. So it is thinking of metabolism as it is a process of converting from, chemical potential energy into another form of energy. Any other ideas? Okay, so I'll define it this way. It is all the chemical reactions in living cells. If you were to add up all the chemical reactions in a living cell, that is what metabolism is. So there are people that have quicker metabolisms than others, but it's not directly meaning that they digest faster than anybody else. What's happening is they just maybe carry out more of these chemical reactions than others. A lot of times people with quicker metabolisms, they generate more heat. Yeah, Micah.
So how does metabolism affect something like blood sugar?
You mean how does your blood sugar rise as a part of that?
Yeah, because I
So
know that for me, overnight when my metabolism slows, blood sugar changes.
that's a good question. Yeah, so when you're sleeping, your brain shuts down certain parts of your body to allow for that rest that your body needs. And as it does is it lowers the metabolic rate. So those cells that are in tissues that are being partially shut down are not going to metabolize as quickly as they do when you're awake. And so what that means is they are not, if they're not processing as much sugar, then there's going to be sugar that might build up in your blood. Although usually what you find is you spend so much time fasting while you were sleeping that your blood sugar drops, just because even though you're not using as much of it, it's still being pulled into cells. And it's been so long since you've eaten, your blood sugar's lower. Make sense?
Yeah.
Okay. Any other questions? All right. Well, so now if we have an idea of whether or not a chemical reaction has taken place, now we need to start talking about what types of reactions occur. Now, this is not going to be an exhaustive list of all of the chemical reactions that are possible. Okay? This is a list of the bulk of the chemical reactions. All right? So, reactions can do a number of things. One is they can require energy, and we call these endergonic reactions. Okay, so if you take a look at our graph, when you get a chance, I just added this type of reaction to what we had already drawn on the graph. Now, our reactants were lower in energy than our products, so if we're going to convert those reactants into products, we have to input energy. And that's why these are reactions that require energy. And so what do you think these reactions would feel like if you were to touch the flask in which this reaction is happening? Yeah.
Cold.
They would feel cold, and why is that?
Because they're pulling energy out.
Yeah, energy is now leaving your hand and going in to drive that reaction. Yeah, Josh?
The same thing happens when you're changing form from like a liquid to solid.
Yes. Well, from a solid to a liquid. Right, so like if you grab ice and it's being transitioned over into water, that requires energy to make that happen, and that energy is again leaving your hand to drive that process. On top of that, the ice is colder than your hand, which energy is also going to flow from a place of higher energy to lower energy.
Yeah. Kind of CO2 cancer.
Oh, yeah.
If you release it, it's
And then, yes. And there it's going from a liquid inside of the canister under high pressure into a gas. And again, that requires energy. And so if you're going to convert from a liquid to a gas, that requires energy, and so it's going to feel cold. All right. Then reactions can, if there are some reactions that require energy, there better be reactions that release energy, right? Especially if you're thinking about metabolism. All of the reactions that take place in living cells. If there are some processes that require energy, there better also be reactions that can provide energy to fuel those. Can any of you think about a reaction that takes place in our cells that releases energy? Yeah, Ethan. Respiration, right? So as we take our food molecules and as we break them down, this is what you were getting at, Thomas, either? Okay. Is as you're breaking that material down, you're releasing that energy. That's why you have to eat. Okay? Plants, they don't have to eat like we do because they harness sun energy, but we can't. Okay? So we get our energy from our food molecules. But yeah, exactly. So breaking those down, which respiration is one of those processes, it's going to release energy. Good. This is an exergonic reaction. So over on our graph here, the red curve is an endergonic reaction. The black curve is an exergonic reaction. All right, additionally, reactions can transfer electrons. We call these oxidation reduction reactions. Reactions that transfer electrons. Oxidation reduction reactions. Reactions can form water and salt. Acid-base reactions do this. This is one of the reactions. We'll do an endergonic and an exergonic reaction in a couple of weeks when we do our next lab, so that you can feel an endergonic reaction. You can feel an exergonic reaction. What would an exergonic reaction feel like? Feel warm, right? It's releasing energy, and if you're holding the glass, it's going to release that energy into your hand. All right? But we'll also do an acid-base reaction. So we'll take a strong acid in lab, and you'll be able to tell that it's a strong acid because we'll use it to, I don't know, maybe clean the gunk off of a penny. And then we'll take a strong base, which you'll know it's a strong base because we'll use it to maybe clean a clog out of a drain. Okay, and so you'll know that these are very strong and powerful solutions. And then we'll mix them together, ensure that they have fully mixed and neutralized, and then your products are just water and a salt. And in this case, it will specifically be table salt. And so if you wanted to, well, actually you can't. But if you weren't in a lab and you wanted to, you could drink it, because all it is salt water at that point. Even though initially it was two very dangerous solutions. Yeah?
It would not be very good for you, though.
Well, I'd probably have some of the material that was cleaned off the penny, right? That's not great. But other than that, like if you just used the same solutions but not the actual amount, maybe you just took some of it out to clean off the penny and to clear out a drain, then it would be fine for you. It would just be salt water, which it's not great to drink a lot of salt water, but it's fine to drink a little bit. And then you could take this and, you could use it to brine something. Or, better yet, to cure a big hunk of pork belly and make some bacon. Right? A reaction can also form a solid that settles out a solution. This is another reaction we'll do in our lab in a couple of weeks. Well, we will take two solutions that are entirely liquid. Okay? That everything is suspended in the liquid. We will mix the two solutions and a solid will form and fall out of solution. Alright? Again, this is not an exhaustive list of reactions, but it's a pretty good list of reactions. All right. So, based on our experiences in this class up to this point, how do you think we will answer this question? What types of reactions occur? C-list. S-E-E space L-I-S-T. C-list. Now, we're going to have another slide that has the same question. We'll just add more information, but you won't need to answer this question again. Okay? So what types of reactions occur? We're still addressing this question, and now we're looking for evidence of it, right? First slide, we talked about how do we know a chemical reaction has taken place. The next slide, we talked about specific types of chemical reactions. Now, for this third slide, we're going to start saying, okay, in these types of chemical reactions, what evidence do you see? So in chemical reactions, we can trace the chemical changes. We can trace the chemical changes. So in endergonic and exergonic, those are fairly obvious. If they're exergonic, we can feel the energy being released. If they're endergonic, we can feel the energy being required. Oxidation reduction, we can determine which reactant is gaining electrons, and we call that the reduced reactant. The reduced reactant. And yes, I understand the irony of calling something that gains electrons reduced, but I did not name these. Is that redundant or not redundant? Is that ironic or is it just like an oxymoron? I don't know. Anyways, the reduced reactant gains electrons. So in an oxidation reduction reaction, we can trace which one gained electrons. We can also figure out which one lost electrons, and those get oxidized. We call that the oxidized reactant. Any of you ever heard the term oxidation? What does it mean? Or can you think of an example of it? Now you know that it means the loss of electrons, right? Oxidation, it's the loss of electrons. But what about some examples? Micah?
It's like when copper comes in contact with oxygen and turns green.
Yeah, it turns green, or when iron comes in contact with oxygen, it turns red. Or the sugar in your apple comes in contact with oxygen and turns brown. It's why an apple browns after you've bitten into it. Okay, you're oxidizing the sugar in the tissue. I don't know if you knew that or not. That's what's going on. Okay, and so what's happening is it's losing electrons. It's also gaining oxygen at the same time. We can figure out which one's the acid in an acid-base reaction because an acid triggers hydrogen ions to form, either by releasing them or by triggering them to be released from water. So we can figure out which is the acid in our acid-base reactions by which triggers hydrogen ions to form. Somebody tell me what's in water, atom-wise. Yeah, Joe.
2 hydrogen, 1 oxygen.
2 hydrogen and 1 oxygen. So if we were to force water to release a hydrogen, what's going to be left? A hydrogen and an oxygen. Look at this. A base triggers hydroxide ions to form. So either by releasing them or by causing them to be released from water. Either way, a base, when you mix it into water, is going to trigger the formation of a lot of hydroxide ions. And an acid, when you mix it in water, is going to trigger a lot of hydrogen ions. Yeah, Micah.
What does the plus and minus sign of the
Charge.
Okay.
Yep. So the hydrogen ion here has a positive charge like protons have a positive charge that we talked about a couple weeks ago. And then hydroxide ions have a negative charge like electrons have a negative charge. Yep. All right. And then in a precipitation reaction, that product, what you find falling out of solution, that is your product. It is something unique. It wasn't there before. And how can you tell it wasn't there before? Because it hadn't fallen out of solution before, right? Which means it wasn't there. Okay? So we've already answered this question. We don't need to answer it again. Don't need to give you any key terms at this point because we'll talk about all of these reaction types again in the future. We'll have a chapter just on acid and base reactions, maybe 2 chapters. We'll have a chapter on oxidation reduction reactions, maybe 2 chapters. So we'll address all of these again. We'll worry about definitions then. All right. Any questions? All right. So we have one more thing we're going to deal with, and that's how do we balance chemical reactions? And I'll tell you in a minute. I'll actually answer this question with some reasons of why we have to balance chemical reactions. Now, the way you're going to answer this question is we're actually going to do it. You're going to do it in your notes, and then so you can just write "see my notes" to answer this question. Okay? But I want to give you a couple of pieces of information first. First of all, we have a law that is a very important law in chemistry. It's called the law of conservation of matter. The law of conservation of matter. And it tells us that we cannot create nor destroy matter. We cannot create matter. We cannot destroy matter. Okay? It's the law of conservation of matter. Again, it's a very important law in chemistry. Do any of you see the implications of this law? Yeah, Joe.
You can't have a chemical reaction that just makes that stuff disappears.
Correct, which means that when we're noting our reactants and our products, we better be able to keep track of all of our matter, because we can't destroy it, and there better not be something showing up in our products that is not accounted for by our reactants. Okay? So we can't just create matter, we can't destroy matter. Any other implications? Do you get the feeling that this makes matter eternal? You can't create it, and you can't destroy it. It sounds like matter is eternal, which is interesting. So this law has to be violated at some point, unless matter is eternal. Which I think a lot of the Greek philosophers that were atheists, that didn't believe in immaterial creator gods, believed that matter was eternal. Okay? But if matter is not eternal, this law has to be violated at some point when you first generate matter. Okay? Then it's a question of what is a more comfortable violation of this law? A random event or an immaterial creator? Anyways. Okay, so what this means is that we need to make sure that the same number of atoms of every element that appears on the left in our reactant side also appears on the right in our products. So if we have 5 atoms of oxygen on the left, we better have 5 atoms of oxygen on the right. Yeah?
Is that excluding nuclear?
Yeah, right. Nuclear reactions get a little bit interesting because there we have an unstable atom that breaks down into a different type of atom. It breaks down into a different element. And so in there, we still have to keep track of matter, but there we have to keep track of the total subatomic particles. We have to keep track of all of our protons, all of our electrons, and all of our neutrons. Right? Remember talking about those? So in nuclear reactions, atoms are decaying. So there we have to keep track of all of our protons, neutrons, and electrons. Those are not created or destroyed. Alright? So yes, that is excluding nuclear reactions. It's a good question. So again, we're going to answer this question, how do we balance chemical reactions? By actually doing it. Alright? Now I will tell you this before we get started, that I will probably not ask you to balance a chemical reaction on an exam, because it can take too much time. I will, however, ask you to find reactions that are balanced and reactions that are not balanced. And I may ask you on a quiz where you have more time and you can use your notes and other people to balance a chemical equation. Okay? But not on an exam, because it just can take too much time, and you'll see that in our very first example. All right? So balance the following reactions. Monosulfur dioxide plus oxygen gas produces monosulfur trioxide. We'll have a chapter where we'll talk about how do you name molecules. All right. So what you want to do when you're balancing these equations is to find the element that is most out of balance. How many sulfur atoms do we have on the left? 1. How many sulfur atoms do we have on the right? 1. That's balanced, right? How many oxygen atoms do we have on the left? 4. How many do we have on the right? 3. That is not balanced. We only have 2 options. One is balanced and one is not. Which is the most out of balance? Oxygen, right? It's the only one that's not balanced. Okay, so we have 4 on this side. We have 3 on this side. We have to figure out how to balance it. The way we do that is we find the least common multiple. What is the least common multiple of 4 and 3? 12. Now, how do we get 3 to be 12? We multiply it by 4. So if every one molecule of monosulfur trioxide has 3 oxygen atoms, how many of these molecules do we need to have 12? 4, right? If every person has 3 hot dogs, how many people do you need to have 12 hot dogs? 4. And then 1 bully to eat them all, right? Have I told you already about the 12 hot dogs and the significance of that? Okay, this will be on the recording, that way you can remember it for the rest of your life. So every year we do a alumni game, and we go to Dodger Stadium. And by the way, I graduated from here at Masters, and we sit in the all-you-can-eat pavilion. And I currently hold the record for the most Dodger dogs consumed in a single game, and it's 12. It was actually 11 3/4, but everybody around agreed to count it as 12, and so it's 12.
In a normal 9-inning game?
Yeah, and what was it? Because they stopped serving them in the 7th inning stretch. So, but somebody had a 12th, because I had eaten 11, and then somebody had a 12th, and they gave it to me in the 9th inning. But yeah, but I was 21 then, so I did try to do this recently, and I ate 3, and that was all I could eat. But at one point, I ate 12, and a thing of nachos, and drank 6 sodas. I mean, it was awesome, but really gluttonous, and I felt really sick afterwards. All right, okay, so we've accounted for this. Now, how many sulfur do we have on this side? 4. Oh, we haven't taken care of our oxygen. Okay, so how do we get this to be 12 over on this side? We've got to multiply 4 by 3, but we don't have all 4 in the same place. Right? So now it's like, ooh, what do we do here? Well, why don't we figure out how to balance sulfur and see if that helps us out? Okay? Now there are 4 sulfur over here. There's only 1 over here. Right? What's the least common multiple of 1 and 4? 4. So how do we get 4 sulfur? Right, we get 4 of these molecules. Now our sulfur is balanced, yes? 4 and 4? Okay, how many oxygen is this now? 8. How many from here? 2 more. So we need to get 4 more from here, right? Here's 8. We need 4 to make 12. If 2 people, if one person has 2 hands, how many people do you need for 4 hands? 2. So if one oxygen molecule has 2 oxygen atoms, how many oxygen molecules do we need for 4 oxygen atoms? 2. All right? Now let's check our work. Do we have the same amount of sulfur on the left as we do on the right? Yes, we do. Do we have the same amount of oxygen on the left as we do on the right? 8 here, 4 more here is 12. 12 here, we're good to go. All right? But look at this. How many sulfur do we have on the left now? How many on the right? How many oxygen do we have on the left? 4 from here, 2 more from here, 6. How many do we have here? 6. That's another answer that we couldn't have got by doing the least common multiple. But we can get it now. And so always be willing to check to see if you can reduce all your numbers. If you end up with all even numbers when you balance a reaction, you can divide all of those by 2. And you don't have to. I mean, it's still balanced, without doing that. But if you are actually going to carry out this reaction, using 2 moles of sulfur dioxide is less expensive than using 4. Do you agree? Yeah. And sometimes expenses are important. So now you see how one of these problems could take a long time if you just keep going back and forth and it throws other things out of balance. Okay, let's do this one. So this is manganese 4 oxide plus aluminum produces manganese and aluminum oxide. Okay. How many manganese do we have on the left? 1. How many on the right?
1.
Okay, well that's balanced. How many aluminum do we have on the left? 1. How many on the right?
2.
That's not balanced. How many oxygen on the left? 2. How many oxygen on the right?
3.
You ready? So which one is the most out of balance? Probably oxygen, because to get 1 to equal 2 is very easy. To get 2 to equal 3 is a little bit more complicated. Right? So let's go ahead and do oxygen. So oxygen, there are 2 atoms of oxygen on the left, 3 atoms of oxygen on the right. What is the least common multiple of 2 and 3? 6. How do we get 3 to equal 6? Times it by 2. Okay? How do we get 2 to equal 6? Times it by 3. Now is our oxygen balanced on both sides? Yeah, this one was nice because all of our atoms were restricted to a single compound on each side. Right? Oxygen is only with manganese on the left, only with aluminum on the right. Okay? Now, how many manganese do we have on the left? 3. How many on the right? 1. What's the least common multiple of 1 and 3? 3. How do we get 1 to equal 3? Multiply it by 3. How many aluminum do we have on the right? 4. Right? Each compound has 2 and we have 2 of them. Okay? How many do we have on the left? 1. What is the least common multiple of 1 and 4? 4. How do we get 1 to equal 4? Times it by 4. Now this one we can't reduce down anymore. 2, 3, and 4 are all prime numbers. Okay? So we cannot reduce these numbers down anymore, although we'll check for that just to make sure. And now our reaction is balanced. Okay? And what you'll find when you take a look at your Lesson 7 worksheet that I just gave you, you'll find that these 2 reactions are in that worksheet. And it asks you to find reactions that are balanced and which are unbalanced. And if we had to work to balance these, it's an indication that they are unbalanced. Right? Okay, any questions? All right. Let me go ahead and cancel this, close this.